All right. Hi, y'all. How we doing? Been a little absorbed in my head up here because lots going on this week. Got a lot of preparation. The grading is a little behind. I haven't got to the extra credit. I know I mentioned to a few that we would, but overall, just I'll catch it up over the weekend. Not a huge deal. We are on the last new thing for the entire semester. So again, as a reminder, like this is it. We're going to do a summary of the course. Then we're going to use those things to dive in some more detail through the second unit before the second test. We're going to go through some more practice problems. We're going to do some more examples, but this is it. After this, you will be able to go and talk with anybody who has passed a business calc course or a Calc 1 course, and you will be able to understand pretty much the conversation they're working on. You won't be able to necessarily do all the computations and the calculations that they can do. That's why we still have more weeks coming up. But this is the last of the story. Like, this is it. So, what are some things? We have gone on a journey where we decided to start looking into how we can answer questions about forever, forever big, forever small, forever change in a moment, do moments change? How do I get close to making area perfect? What about area of curved regions? Like, all of this is just how do I deal with forever and utilize it as a tool in combination with my algebra. This here is going to be the culmination. It's going to be pretty much a review of what we have discovered over the last 2 weeks. And then on top of that, it's going to be a very good example for us to start to recognize that a lot of these problems, the difficulty is not in the computation. The difficulty is in figuring out what it's even asking. And that the best way to figure out what it's even asking is to try to understand the story behind the symbols. Once you have that, especially in today's lecture, it's going to go by like this. Like, it's going to take us about 20 minutes to figure out what these questions are asking. It's going to take us about 2 lines of work to solve them. We're going to solve it in like 5 seconds flat. It's going to take us 20 minutes to figure out what we're even doing in the first place. So it's a good time to practice and understanding the symbols and the meanings behind them. Let's introduce, or I should say reintroduce, the main player of this topic. This is Leibniz. Leibniz is one of 2 people credited for formalizing and compiling the patchwork that is calculus. Between Leibniz and Newton, we get most of our notation, we get most of our theory, and we get a lot of our conclusions. So let's talk a little bit about Leibniz here. Attended university by age of 14. Completed a bachelor's degree in philosophy in a single year, wrote a book by age 19, was 21 by the time that he became a lawyer, worked as a lawyer for 6 years, and then picked up mathematics mostly as a hobby, worked with mathematics for the next, we'll say, about 4 years, sending letters to Isaac Newton, trying to understand more of his approach, and independently of Newton, discovered calculus and all of the exact same things that Newton did. Then turned 30. So again, we're talking about people just exploring actively these topics. Like, these are interesting, like, driving topics and questions, and the concepts that they're coming up with are nothing that is monumentally above any of us. Like, they weren't geniuses in the sense of they just simply had better ability to solve big problems. They just had a passion, they saw a pattern, they used the insight, and they got answers. And now we all thank them for it and use it just about every day when we analyze the world around us. So let's do a little bit of a reminder of what we have talked about between Wednesday and Friday. So remember, we have different equations that described how things move. If I drop something from free fall, it will fall according to gravity. So its acceleration is gravity, -32. -32 means -32 feet per second, meaning if I wait a second, it will be going down -32 feet per second more than it was before. So if I clock it with a speedometer, it's going -32 feet per second after the first second. It's going -64 feet per second after the next second, and it keeps on ramping. And then we looked at how we can use the fact that it's traveling at a speed to figure out where it is in space. So all this together gave us the graphs that we played with. We started off by saying -32 is our acceleration. based on how much time passes. We took that as an area and said that I could take all of that area together and I could make a brand new equation. That equation has to be one that steadily ramps in velocity. So that's where our velocity equation came from. Then we took that as an area and said we have a bunch of velocity times time represented here. Speed times time gets us, no, think about it. Miles per hour times hours gets us miles, right? Distance. So we've got this right here. If I look at the area for velocity, that's a bunch of tiny little rectangles whose height is speed and whose width is time. Speed times time gets me distance. So that's where we were able to get our last graph and saying that our distance, our position, must be ramping down faster and faster. This is all that we need to be able to understand one of the biggest and most fundamental theorems of calculus. So before I go on, does anybody have any question about where these equations came from, how we use these equations to make each other, and the logic that connected them? I've got a lot of time prepped in here, so we're good for lots of questions. Go ahead.
Why is the 32 divided by 2 in the equation, in the last equation position?
Sure. So it came from trying to find the area of this, which was a triangular region, right? So that came about from, okay, 1/2 base times height. The base here was however much time has passed. And the height was, well, -32 times t. That was the equation we had. So at every moment, it was -32t. When you multiply all that out, you will get the -32 divided by 2 and the t squared. Good question. Any others? Okay. So we have a connection. If I am taking acceleration, I can add up area, get to velocity. I can add up area, I can get to position. That takes me sort of down this ladder. Then we also know from our algebra that if I want to talk about how position changes, that's speed, and how speed changes, that's acceleration. So what we have is a connection between position, speed or velocity, and acceleration, where I was able to go from acceleration to velocity using integrals, aka finding area under a curve. And I'm able to look at how position changes up to velocity by doing derivatives. So we did this through one example and quite a bit of story. The question is this true all the time? Like, does this actually work? Are derivatives the opposite of integrals? Are integrals the opposite of derivatives? Because if they are, then we have the ability to use everything we discovered from one to better understand the other, and everything that we understand from the other to better describe the first. So we need to find a way to kind of understand, is this just a one-off case, or is this in fact true? So we're going to need to kind of pull in some notation. This is the same notation we had before. I just want to collect it for us. Remember, if I write d with something next to it, like dt dx, that means that I'm talking about a forever small change in blank. It's representing an infinitesimal. An infinitesimal means the idea of trying to capture the next moment. We all understand that that's not able to be done directly, but that's still the idea. Like, how much am I changing right now? Well, then it's like, how much am I changing in a moment? We can't hit that directly, but we can still talk about it. So we have a notation here. D blank means a forever small change in, just like our dx and dt. We also have d over dx. This right here means I'm trying to take the derivative of. It means I'm trying to consider how whatever this could be area. How does area change as x changes? It could be velocity. It could be, how does velocity change as x changes? It's saying I want to consider the change of something. And then lastly, we have integral. Integral means the complete, the total, the perfect area, the area under the curve. We're going to be using these and just building a story all for the hour. So does anybody have any question on what this notation means or where it came from? I'm hoping this is starting to feel a little bit like a review. Okay. If I wanted to figure out if subtraction is the opposite of addition, a nice way to do that would be, well, if I add 2 and I subtract 2, it should be like I did nothing at all, right? So I can figure out if subtraction is the opposite of addition by saying, you know, I added 2, let's subtract 2, I'm back down to the beginning. That'd be like versus multiplication. If I said add 2 and then multiply by 2, that would not cancel away. So like we know that multiplication is not the opposite of addition. We can figure out division is the opposite of multiplication through the same idea. Let's multiply and then divide. And we see that that becomes redundant. So it's like, good, they undo each other. Excellent. Except division undoes multiplication-ish, right? Multiplying by 0 cannot be undone by dividing by 0. That doesn't work. So every once in a while, we have some stipulations, some details about what happens if we try to cancel away. But if our theory is that derivatives are the opposite of integrals, then the best way to prove that they are opposites of integrals is to do the derivative of an integral, and then to later try doing the integral of a derivative. In the same way that we're going to try to do addition and then subtraction versus subtraction and then addition. It should all help make these problems simpler. So that's what we're going to do today. There's 2 parts. The first time, we're going to try to do integrals of derivatives. And the second time, we're going to do derivatives of integrals. Now we're going to see what happens. All right, part 1. We're going to do the integral of a derivative. The biggest challenge of these problems is figuring out what this even is. What does this mean? So the biggest suggestion I can give you all is to build the story behind the symbols. Let's break it down. So we have integral. Integral means the total or the complete or the area. All of that is fine. Derivatives. Derivatives are talking about change, the speed of change. So we've got speed. And then we have time, dt, very small amounts of time that I'm going to multiply by speed, and then I'm going to add all of that up. So my question to you all is, what is speed times time? Be careful. Give yourself units if you need. Speed, what's a way we measure speed?
Miles per hour.
Miles per hour, great. What's a way that we measure time that goes along with that speed? Hours, good. Miles per hour times hours is? Good, distance. So we have speed times time is distance. So I'm looking at the total distance. The total distance. I'm just trying to figure out the total distance that's happened in a story. That's what this is saying. Let's do an example, will help lock it all in. So let's imagine we'll actually give ourselves an equation. Like, let's imagine that this is an equation that means speed. All right, so we're going to play around a little bit. This right here says that I'm trying to find the integral from 1 to 5 of 2t dt. That we can think of it as speed and time and trying to find a total. But at this point, maybe it's good to get our eyes involved, because integral means what again? Sum of or total or area or area. I can draw area. Let's draw area. All right, so let's go ahead and draw a little graph. What's the equation? 2t, good. So let's go ahead and graph 2t. That's going to be a line that goes up at a slope of 2. So I got 2t. What's the axis then? Is it x here? What is it?
That's time.
It'd have to be time, right? Otherwise, it wouldn't make sense that as time goes on, this thing goes 2 times higher. So this has to be time. Good. So we're trying to find the area. What do we do with this? Who can help me? Integral from 1 to 5. What does that mean? Please.
We need to find the area between 1 and 5 on the graph.
The integral between 1 and 5. The area between 1 and 5. All right, there's 1. There's 5. There's the area. All right. Are we feeling good? Feeling like I haven't violated anything that we talked about before? I'm just kind of putting down on the paper exactly what we talked it was going to be about on the paper. Okay, good. So this is speed, and I'm trying to look at how much distance I've traveled, because remember the meaning we have from this is find me the total the total distance traveled, how do I do that? How do I figure out this area?
Well, from what I can tell, what you need to do is that you need to take the sum of 5 to 0 and then subtract it by the sum of 5. Sorry, the sum of 1.
So we could look at it as how far did I travel in 5 seconds versus how far did I travel in 1 second? And then the difference between how far I travel in 2 seconds versus 1 second should tell me how far I travel between 1 second and 2 seconds. Cool. How do we do that? Let me throw it around. Let's start getting some other hands. How do we do these integrals? Please.
Do a Riemann sum between 0 and 5.
We could do a Riemann sum, right? Fill in a lot of rectangles, make those rectangles skinny, maybe bring in some summation notation. Oh, but that took like 40 minutes. So yes. Is there a way of doing the Riemann sum, getting the answer of Riemann sums, but getting it faster?
Power rule?
Power rule. Power rule is literally going to give us the same answer as Riemann sums. It's backed up with the logic of Riemann sums. It's the same thing. We'll just do it through the power rule. All right, so power rule, let's see, let's bounce. Who else can remember power rule? Talk to me about power rule. Please. Increase the exponent by 1. So I went from, this is a 1, I'm going to make it a 2. Divide by the new exponent, and then the 2 comes along for a ride, right? Good. So I got that right there. I still need to plug in 0 to 5. That's fine. And then this one here, again, same pattern, right? In fact, same structure. So that means t squared, where I need to plug in 0 and 5. Take away t squared, where I need to plug in 0 and 1. I think that's 25 minus 0 minus 1 minus 0. So it's asking me how far I travel between 25 and 1. That'd be 24. There we go. Other ways we could have solved this problem. We could have absolutely solved this problem by just recognizing that, like, this is a big triangle, right? So if you wanted to find me the little region in here, you could have done some geometry work. I'd be okay with geometry work. You say that region right there is big triangle minus little triangle gets me region between triangles. How big is this triangle? It's a 1 by however high it'd be, plug in 1, that'd be 2. It'd be a 1 by 2. No, that'd be the big one, sorry. That'd be 5 by plug in 5, 10. 5 by 10, and this one here would be a 1 by 2. You do 1/2 base times height, take them away, same answer. Same answer. Yeah.
Would the other piece be a rectangle? Or
I'm looking at this piece right here, taken away from that piece right there.
Oh, okay.
Yeah. Right. That's okay, great, right? There's another way you could do it. You could do it by saying, what if we just power ruled from the beginning? After all, we already proved we could power rule from the beginning. That might be the shortest way of solving this. The shortest way of solving this is saying, I'm going to do the integral. When I do the integral, I just do that power rule. So let's do the power rule. Increase the power to 2. Bring along the 2, divide to compensate. And I need to plug in the bounds, 1 and 5. If you plug that in, you get 25 minus 1 is 24. There you go. Like 2 lines of work. The exact same problems we've been exploring. So there's a summary of what we've got right there. Here's the story we went through, and then I'll get right to you. So here's the story we went through, right? The integral of a derivative means I'm looking for the total of a bunch of speed times time. A bunch of speed times time is a bunch of distances. So I'm looking for total distance. How do I figure out total distance? I compare my final position versus my initial position. So if I ended on 25 and I started on 1, I have traveled 24. That's it. That's all we're doing. We're just looking at how I moved, because that's what the question asked me for. How much did I move? What's my total distance? Did you have a question?
Yeah, just going back to the last part we did on the last slide.
Sure.
You did like the 25 minus 1. Where did
Yep.
you get the 1 from that equation?
It's the same solution I have here. So we use the power rule. So the power rule is where we increase the power by 1 and then divide by the same thing. Again, if you're looking for a mnemonic, here's my mnemonic. If you're building area, build the power. That's my mnemonic, right? That's how you can remember it. If you're ever trying to build area, right? You're ever trying to do an integral, build the power up. That's the power rule. So we're trying to do the power rule that gets us this structure. And then this structure just says I'm looking, this is my position right here. This right here is the structure that tells me where I am, my position. So if I want to figure out my position at 5 seconds, I'll plug in 5 seconds. If I want to look at my position at 1 second, I'll plug in 1 second. If I want to look at how much I traveled, I look at where I am versus where I was. That's my travel. We're all good? All right, let's see where we go with this. Let's again, same example, same story. We're going to play with it. We're going to see what happens. So I've got the change. That's right, there's change. Change in my total area, where the area is speed times time. Okay, that's all I'm doing. I'm pulling out the exact same thing. Ooh, okay, so again, let's get our eyes involved. Let's get a graph. T is my function. What's this axis? The horizontal axis represents what here? Time. Good. Very nice. Looking for somebody who hasn't participated yet. Help me out. How do I put this in my picture? Integral from 0 to x. How do I put that in the picture? What's that mean and how do I draw it? Please. Zero here and like x is somewhere else. And then what are we doing with the integral? Good, we're taking the area, right? Excellent, excellent. So this right here, that's my area. My area from 0 to x. So that's taking care of this whole bit. So now I have that off to the side. That's my area. ddx of area. All right. ddx, that's me trying to change something as I change x. Let's make that nice and clear in the picture. I'm going to change x. How much? By dx. I'm going to change x. In doing so, we're trying to figure out if I change my area. So I've changed my x to maybe something over here. Look at this new area. I've got a whole bunch of area here. That's my change in area, my dA. The only difficulty is that d is supposed to mean forever small change in area. Are we all seeing that this looks like a pretty big chunk of area? Right? So like my drawing's not perfect. My drawing's got too much. But if I make it perfectly small, I'm not going to have much of a drawing to show you all. Because if I make this forever small, forever skinny, then all of a sudden my rectangle, like my it's just right there. Like it's just tiny little thing, right? Tiny little change. I got to bring that x value in. I got to make the change nice and small. So let's draw a little bit of a picture to help us clarify this. So this currently is my change in area. There's my dx. There's my dA. I've got a y value I started at, and I've got a y value I finished at. That's this blue region. I just grabbed it and put it down there for my picture. The problem is again, that's too big. I need to make it smaller. If I bring dx to something much more reasonable, like something close to 0, since it's supposed to be a forever small 0 type thing, then that means that I'm going to be bringing in this side. I'm going to be bringing it in. So then if I bring that all the way in, this y2 value is going to get a little bit less and less and less and less until it approaches what?
0.
It won't get to 0. That would be if I brought it all the way back down to the height of 0.
It approaches x.
X isn't a height. X is just a sideways position.
It approaches y1.
It approaches y1, right? If I'm making that area skinny, then I'm bringing in that area that area, the y2 hits the y1. So that means that this right here is kind of what it's going to get closer and closer to. It's going to get closer and closer to where this y1 value doesn't change, but this other one gets pretty close to y1. And then that makes a more accurate drawing for dx and dA. So it's this idea of saying I'm bringing it in. All right. So I've got an understanding of the picture that's supporting this. And this says I'm looking for how my change in area compares to my change in x, right? That's what it says. That's what I was trying to figure out this whole time. You ready for the big mind-blowing reveal of why I organize the semester the way I do and why I have you all start with the drawings I have you start with and why I encourage you all to do the techniques I encourage you to do? Because what's my favorite shape, y'all? It is a rectangle. What do we have that we are currently looking at in our picture? It is a rectangle. And this right here says I want to divide area by width. Do you all remember that when I was talking about division, I said we can use rectangles for division? That dividing by like 16 divided by 2 corresponds with a picture where a rectangle size is 16 units. I'm dividing it by 2 and just asking what the other side is. Do we remember doing that? What would the answer here be? 16 divided by 2 is? Because 8 times 2 gets us back to that rectangle, right? Well, this right here says I want to divide the area by one of the side lengths. Here we go. Here's the area divided by this side length. What's the other side? That's it. So let's recap a little bit. What is this saying? It's saying, how am I changing my area when I compare it to my change in width? And we say, well, if you change the width, the only other thing that affects the area is the height. So this is a big, complicated, symbolic way of them asking you, what is the height at the end? And that's all it's asking, is what is the height? So here's the question for you all. Here's x. There's the height. What is that height? Close. The position is x. What's the height? How do I go up to the graph?
2x.
I plug in x. Exactly right. Done. This is infuriating how simple this question is. That literally all it was asking us was, what is the height at the end? And we say, well, you plug in x and that's your height. So there's your summary. The change in an integral of something is saying, how am I changing my area compared to x? Well, that's a change in area when I'm trying to divide away a width. That leaves you with a height. So how do we solve these problems? If you're doing a derivative of an integral, then that means what's my height at the end? So you plug in the thing at the end. And that's it. I'll pause here for a moment. Any questions? All right. So again, like, is this something that like symbolically is a lot? Sure. But also like, and it can get frustrating when it's like, really, like, that's all that I'm doing. I'm just plugging it in. It's like, no, what we did was the story. What we got was the result of plugging it in. But like, sure, if you want to ignore the whole story, that's fine. We're going to build on it later. So that's not a great strategy. But it is about the story. And it does make sense why it would be so simple, because imagine if I went up to a third grader and I said, today, I'm going to give you a problem where I multiply by 64, and then we're going to divide by 64. And they're going to be like, oh, no. It's like, no, actually, it's quite easy. You don't change anything, right? Like, it's going to be intimidating when you look at it through the steps. But when we understand that they're undoing each other, it kind of makes sense why it would be a really, really simple answer, because we've undone a good amount of the story. They're opposites. It should make it simple. Right. This is the last bit that I have for you all. After this, you have all of calculus, at least in topics. You've got it all down pat. My biggest suggestion is do not try to memorize the ways I solved problems. Go back through and retell yourself the story as to why I solved the problems. Because this is what we've done now, right? Next, if we're going to summarize, we started with the invention of numbers. What are numbers? They're quantities. Some quantities are difficult to touch directly, like pi and e, square root of 2, square root of 5, square root of 3. Anything with square roots, pretty much the entire irrational category. So we've been describing these answers as approaches for a while now. And now we're just sort of starting to recognize it and formalize it. So how did we approach these problems? We tried hitting them directly on, right? The method of exhaustion. Let's just try to approach things directly. It gives us insight. But as some of you probably got for the quiz back, if you tried plugging in numbers for those limit problems, it's not full credit because you're never done with that strategy. You can never plug in something big enough. You can never get an answer correct enough as long as you are in the list. We have to go past the list. We have to understand how the list is behaving and where the list would converge. And then we took that and we used that as a way of going back through these problems of antiquity, finding out how big things are, getting area pinned down. We introduced derivatives. Derivatives was trying to look at the change in a moment, which is paradoxical itself, but something that we again can get if we allow ourselves the ability to start a little bit wrong and work our way towards correct. And then lastly, we have the fundamental theorems of calculus. The idea that the area that a graph contains is actually an opposite story to how quickly that graph is growing or shrinking. And it makes the most sense if you look at it through Galileo's exploration of saying, I am trying to just simply turn acceleration into velocity, velocity into position, and then recognizing that if I want to change position, I'm going right back up that ladder. So I've got plenty of time after class. I will stick around and happily answer any questions you have about the homework, about your guided notes, about literally anything in concerns to this class. Stick around with any questions. Thank you all. See you next week.